In this unit, we're going to be learning a whole list of integration techniques to help us integrate expressions that are just slightly different from one another. And so if we kind of do a quick review here of what we already know, we started out with just straight integration, and then we get a little more complicated with something like this. And the idea here is to get you to look at characteristics to see what can be done to maybe get rid of the numerator and simplify the expression. So in this situation, we want to be cognizant of this polynomial in the denominator here being differentiated, and when we differentiate it, we end up getting the numerator. So this one would fall into a U subcategory in terms of being able to solve this integral and set it up to be a more simple expression. So we might say something like U equals t squared minus t plus 2, and then our differential expression du then is found by differentiating that expression, and so we end up with the numerator of 2t minus 1 dt, which happens to be that whole expression. So this one could be really simplified into a 1 over u du, which is something that's really simple to integrate. So the idea, like I said, is to get these major characteristics and be able to identify them quickly. In the next example here, number 2, we have a classic pattern here that looks like a Pythagorean expression, something squared plus something squared. So if we can rewrite the denominator as 2t minus 1 quantity squared plus 2 squared, then it falls into that pattern that we know from our trig integrals of being a u squared and an a squared. So this falls into that basic pattern of u squared plus a squared du. Some people call that a front of the book because we find those trig identity derivatives and integrals in the front of the book, right inside the front cover, which ends up being an arctan when we integrate this. So again, it's looking for that pattern that we see in integrals. Likewise, we took a look at this one, and it's kind of like that first one. We see this expression down here. We know we can differentiate that and get whatever is in the numerator. So here we have another u sub again, where the u is the x squared minus 4, and then the du is the 2x dx. And so we need an opposite du at the top here, and so we end up with something like 1 over the square root of u du with a minus sign. Because we have a minus sign here, we have to carry that through the expression. And then that's just a power rule. So recognizing those types of substitutions is key to recognizing these things. And so here we might substitute out the 3x here, and then do yet another u sub and then we just have a secant tangent, which we can integrate directly from the front of the book. So another front of the book here, those identities that we can integrate and differentiate. And this also, here's our arcsecant, again, the front of the book. Our arcsecant expression, and that's that classic kind of something squared minus something squared, so it looks like kind of almost a Pythagorean sort of pattern. So that's kind of a real quick summary of what you probably encountered last year. And so we're going to kind of build upon that and go through a bunch of examples just to get that comfort level back again with making those sort of substitutions. Here are some basic steps that you can use too if you like to kind of follow a protocol, so to speak, of easiest to do to most complicated in terms of integration techniques. So you can kind of use that as a checklist and start out with the easy stuff, and if that doesn't quite fit the pattern, then move on to the next complicated process and so on. And so we're just going to kind of go through several of these on the list to refresh our memory of how to do these things. So we look at this and we recognize that as a front of the book. That's just an arctan, so if we want to get it to look really a lot like the front of the book, we'll pull out the 4 because the front of the book just has a u squared plus a squared pattern in the denominator, and so the u is the variable of integration, the a is a constant, so we're looking at that pattern there. So we're looking at 4 times the quantity 1 over a, so that would be 1 over 3 arctan u over a, which would be x over 3. And then, of course, anytime we do this process where we don't have upper and lower limits, that's called antidifferentiation. So we always have a constant of integration that shows up that we need to include. In the expression. So looking on the next example then, here we have a pattern where we have a kind of a reduced power in the top. So we have an x squared in the bottom and x to the first in the top. That should be really a big red flag to use a u sub, because when we do a u sub, we pick the higher power, and when we differentiate that, we can get a lower power. Differentiation is basically a power reducing process. So this ends up being 2x dx. This ends up being half as much as you need here. So the u sub then would look like 1 over u. I need a 4x dx. I have a 2x dx, so I need a 2 du here. And so we're looking at 1 over u du, one of my favorite integrals. So we're looking at 2 times the natural log of u plus c. And then, of course, we have to substitute back into our original variable of integration. And u is x squared plus 9, so it's the natural log of the absolute value of x squared plus 9. You may recognize the absolute value of x squared plus 9 as always being positive anyway. So the absolute values are a bit redundant, but we like to put them in just for good measure. On this next example, number 3 here, if you notice, the numerator is bigger than the denominator. That's kind of a tough one. So we would consider this an improper fraction. And so an improper fraction, like maybe 17 over 4, can be rewritten as 16 1/4, which is a mixed number. And the way we rewrite that is we do long division, right? We would take 17, if we were back in grade school, divide it by 4. 4 goes into 17 4 times. Wow, that's a bad mistake. It's actually 4 1/4, which is 16. And then we have a remainder of 1, and that becomes our proper fraction. So 4 1/4. So we're going to do the same thing on a polynomial level. We're going to take the numerator, which in this case is 4x squared, and we're going to divide it by our denominator. In this case, that's x squared plus 9. And so I'm going to complete this polynomial. In other words, I'm going to write out all the 0 terms in decreasing power all the way down to our constant term. And then I'm going to figure out how many times x squared plus 9 goes into 4x. 4 is bigger, that's why this is viewed as a bigger number. So this goes into 4x squared 4 times. So 4 times x squared is 4x squared. You're basically just trying to match up that first term. 4 times 9 is 36. And I actually am going to get rid of that 36 and move it over to the constant column, because that's really what we have to subtract it from. And so we're going to have to subtract that from above, just like we did here. We subtracted the 16 from above. So we've got 4 minus 4 is 0, and 0 minus 36 is negative 36. We have a number here that it has a lower power of x than what our denominator has. So we now have just like a remainder that's smaller than 4. This negative 36 is smaller than x squared. So we have an improper expression that looks like 4 plus a negative 36 over x squared plus 9. And that becomes our mixed fraction, so to speak, like our 4 1/4. And so really we're integrating that. And if we integrate that, now it's not so bad. Integrating the 4 just gives us 4x. Integrating this, we go back up to that first example. So that's going to be a minus 36 times the integral 1 over x squared plus 9 dx, which happens to be exactly the first example. So this ends up being, and I'll get the plus c on there in just a second, 4x minus 36 times 1 over 3 arctan x over 3 plus c. And you can simplify that as well. So as we take a look at this example, we can see that we have a numerator that's bigger than the denominator, so this is going to be a long division. So again, going ahead and saying we're going to figure out how many times x minus 4 goes into 2x. And so x goes into 2x twice. And let me just complete this polynomial in order of decreasing degree. So we've got 2x minus 8. And I'm going to subtract that from above. So 2 minus 2 is 0. 0 minus a negative 8 is a positive 8. So the mixed number looks like 2 plus 8 over x minus 4. So there's the improper fraction, or there's the mixed number. Excuse me, I said that wrong. And so when we integrate that, then integrating 2 gives us 2x. Setting up the integral for this, I'm going to pull out the 8, and we're going to have 1 over x minus 4 dx. You could do a u sub on this if you want to, but 1 over anything to the first power is just going to be a natural log. So if you don't want to go through the steps of doing a u sub, that would be a reasonable expectation, or that I would be able to expect a Calc BC student to do, is just to skip that u sub. So we know we have x minus 4. A quick check on the derivative of that for the chain rule. We have a derivative of 1, so I'm going to leave off any details about a chain rule there. And so you have 2x plus 8 natural log of the absolute value of x minus 4 plus c as the answer there. Looking at this example, you might look at the denominator and see the t squared and try to differentiate that and say, oh, well, if I take a derivative of t squared plus 1, I get 2t. Which you do, but if you notice there is no variable t in the numerator. So that tells you right away that a u sub is not the most appropriate thing. This falls again into that front of the book pattern, and I keep referring to the front of the book because, you know, in a traditional sense, right inside that first cover you have derivatives and you have integrals of common trig terms. And this falls into a trig pattern. Anything that looks kind of like a Pythagorean theorem expression will fall into a trig pattern. So in this one, we're just going to go ahead and use that front of the book identity, pull out the 3 to make it even look more obvious. So you definitely have an arctan here. So you're looking at 3 times 1 over a is just 1 over 1. That's, in fact, I can even put the 1 squared there to really make it look like the front of the book. So a is 1, arctan u over a, and so that would be t over 1 plus c. And of course, you know, that leaving it like that is just fine. You could clean it up a little bit if you wanted to, totally up to you. So we're looking at that expression for the integral for that. So I bring this example into the mix here, and just as another way of asking the question in a different way, but really it doesn't mean anything different than what we're doing. Solving a differential equation means separating the variables and setting up the differential expression and integrating. So in this situation here, we're talking about the derivative dr dt, and we're going to put the differential expression dt on both sides. You can kind of think of that as multiplying both sides by dt. It's not really a multiplication process though, but if that helps you kind of rationalize what to do, that's fine. And so these differential expressions would cancel each other out, just like just in the same manner that a fraction works algebraically. And so we're left with a differential expression, 1 plus e to the t squared over e to the t dt, and then we can go ahead and integrate that. Now we can sit here and look at this and say, okay, how can I simplify this to make it something easier to integrate? And you know, integration techniques are all really just basically being able to identify patterns and then use those patterns to simplify the expression so that it is easier to integrate. And in this situation, we have a single expression in the denominator. And so what we know then is anything in the numerator can be split apart and put over its own denominator. So, and that's really effective because then we can get some canceling to occur that we couldn't normally get to cancel in this form. So the first thing we need to do is expand that. Remember, expansion was one of those first options to try on that list of things to do in your basic rules list a page or two ago. And so I'm going to go ahead and FOIL this. So that is going to be 1 plus 2e to the t plus e to the 2t, right? E to the t times e to the t is e to the 2t over e to the t. And now we can, I call this process divide and conquer. I'm going to make 3 separate fractions, each with its own denominator. And so this is really going to look like 1 over e to the t plus 2e to the t over e to the t plus e to the 2t over e to the t dt. And don't forget the use of parentheses there, since we have a pretty complicated, multi-term expression. And then we can simplify. 1 over e to the t, in fact, 1 over e to the t I'm going to write as e to the minus t. We get canceling here, so this is really just 2. And we get canceling here, because we've got e to the t times e to the t. So this just ends up being e to the t. And so this is really what we have to integrate, which is far better than what that other expression was. So integrating this, we just get our minus e to the minus t. Integrating 2, that's a plus sign. Integrating 2, we get 2t. And integrating e to the t, we get e to the t. And then we put on our integration, or constant of integration at the end. I wanted to show you this graphically because I think you can probably tell me what the answer is just by looking at it graphically. graphically. So sometimes it really pays to graph if you're able to use a calculator on these questions. We have sine squared t cosine t, and so here's the graph of sine squared t cosine t, and we know integration is an accumulation process. It's just finding the area under the curve. So if we look at the area under the curve from 0, which is right here, to pi, which is right here, we notice that we have what looks to be an equal amount of area above and an equal amount of area below. So since we know that in integration we can have positive area and negative area, then we know that really after we integrate we should get a value of 0. So we'll take the integration process through just to kind of verify that. But sometimes it does pay just to graph it and see if you can find the answer using symmetry or just conceptually without doing the math at all. So looking at this, again, you see that sine of t is raised to the power of 2. So that also should be a red flag that should be a u sub. Anytime, like I said before, differentiation is a power reducing function. So it reduces powers. It also changes sines to cosines and etc. So if we take a look at this and say, well, let u equal a sine of t, then when we take the derivative of u, we can take the derivative of u, call it cosine t dt, and that entire right-hand portion of the expression then can be substituted out completely. So this substitutes then into a u squared du. For the time being, I'm going to leave the limits of integration off. We could find them, but I'm not too concerned about them. I'm going to substitute back in terms of t at the end anyway. So integrating u squared, we get 1/3 u cubed. And of course, no constant of integration because we are wanting to find a value here. So sine of t cubed, and we're going to evaluate that from 0 to pi. And so when we do that, we get 1/3 of sine cubed of pi minus sine cubed of 0. And both of those happen to be 0. So we get 1/3 times 0, which is 0, which confirms what we see graphically. Just to kind of summarize the techniques that we went over today, U sub, these are really all AB techniques. Trig identity is an AB technique. Long division, I'm not sure how much of you did of it in AB, but I'm sure you did a little bit of it. Divide and conquer, these are all AB techniques. Completing the square we didn't do, and they've really de-emphasized that in the BC curriculum, so we won't be doing that as part of this lesson.